Right. So in the last lecture, we looked at solutions of the field equations for a homogeneous isotropic metric, which meant that the metric was the Robertson-Walker form, right? And as we were discussing a moment ago, this is, of course, a starting point for discussing things like cosmological solutions, in the sense that this should be regarded as the zeroth order term in an expansion, where you can, in principle, look at deviations from homogeneity and isotropy, and that would be done by writing the general metric as a background metric, and the background metric in our case would be the Friedmann-Robertson-Walker form, and then you write a correction, you add an h mu nu term, where this h mu nu is supposed to be small. And so that leads to the general relativistic theory of field and density perturbations, which is a very interesting subject, which unfortunately we won't have the time to get into in the framework of this class. But in principle, you can, I think, there was a concern at the end of the last lecture that some people said, this model seems to be a little bit simplistic, right? Because you assume that the universe is the same everywhere. And yes, that is indeed true, but in this case, you are using it. If you wish, you're considering this as a zeroth order term in expansion, when in principle you can take higher order corrections into account. So the consequence of this is that for now, we are going to focus on just this metric and see where it leads, what kind of results it gives. And it is parameterized essentially by the scale factor. And there is this additional parameter k, right, which you remember, for a closed universe, k is equal to 1. For an open one is -1. And for so-called flat universe, k is equal to 0. So there's just this k is just an integer, right? And so we have functions r of t. And as we discussed in the last lecture, we have, as opposed to the static isotropic case, in this case we have matter that is floating around in this universe, and this matter is described by the simplest possible form we can think of, which is, again, in agreement with the homogeneity and isotropy assumption, and that is the form of perfect fluid, which means that we're going to have a function rho, and at this stage, to zeroth order again, rho is the same everywhere, and it's a function of t only, and there is also a pressure that is associated with that, right? And so we are going to end up with what look like 3 equations for 3 functions, but in fact it's just 2 equations for 2 functions, because generally the pressure P is sum W times the rho. In other words, it is given by some equation of state, and we'll come back to that in a moment. The most interesting cases are non-relativistic matter, where W is essentially 0, relativistic matter in whatever form, radiation or neutrinos, where W is 1/3. And in fact, the case of the cosmological constant falls into this category as well by having W equal to -1. So anyhow, you plug this into the field equations, right? And so the field equations, again, are r mu nu minus 1/2 g mu nu r minus lambda g mu nu is equal to minus 8 pi g times t mu nu. So this is our perfect fluid form, right? And the lambda term, we should add that as well. I think for now, occasionally we just focus on the case lambda equal to 0, and then we'll come back to the case of non-zero lambda. So we'll come back to this. And so lambda is small, right? So it will be, in a number of cases, will be quite adequate to set lambda equal to 0. That, as we shall see, applies to the case of the early universe, where the lambda term is completely irrelevant, right? It turns out the lambda term is important at later stages in the cosmic evolution. So you plug this into, as we discussed last time, you plug the Friedmann-Robertson-Walker metric into the field equations, and you get an equation for the scale factor. And I sent you some emails regarding how you do that, right? And so that's a straightforward calculation. It is actually quite easy in this case, because as you saw, there's very few components of the affine connections that are non-zero, right? So the metric is diagonal, right? Only diagonal entries. Some of the entries are trivial, like this coefficient is 1. So it's very easy calculation. And so we end up with the field equations, which I'm going to write over on this side. Right? So the first equation is that 3 times k plus r dot squared divided by r squared is equal to 8 pi g times rho plus lambda. Right? So that's the first field equation. In our case, this is a TT equation. Right? The TT equation. There's only 4 equations altogether because the metric is diagonal and the Ricci tensor happens to be diagonal also. So any of diagonal matrix elements are non-vanishing. So we only need to worry about the RTT and the RRR equation. And the theta and phi equations, in fact, will be identically satisfied once the first 2 are satisfied. So the second one is the RR equation, right? And so that is 2r double dot divided by r plus k plus r dot squared divided by r squared is equal to minus 8 pi g times the pressure plus lambda. So this is the RR equation. Right? So these are the 2 fundamental equations that you get out of Einstein's field equations. And this is essentially the curvature contribution. Right? The left-hand side is what is coming from the r mu nu minus half g mu nu r. Right? And what I've done here, I've actually moved the lambda term over on the other side because the lambda term, well, as we shall discuss later on, and as you realize already from what we talked about previously, the lambda term is some sort of a source term. Right? It's a vacuum energy that tends to act as a source. So it is, I think, useful and perhaps nice to move it over on the right-hand side of the field equations. And you see, I've also written things in such a way that you recognize that essentially this term appears here again. Right? This term appears again. So that means that, in fact, we can replace this using the first equation. We can replace it by a term which involves rho, and of course the lambda as well, which means that you can then isolate the second derivative of the scale factor, isolate it by itself, and write it in terms of p and rho. Right? So we'll come to that in a moment. So this is, if you want, equation number 1, equation number 2. And equation number 3 is going to be energy conservation. Right? And energy conservation or continuity equation. The continuity equation in this case gives that rho dot plus 3 r dot over r times rho is equal to minus 3 r, again, r dot over r times p. This is the energy conservation equation. Again, there's 4 equations, but only one is of interest, the naught one or the T1, because the other ones just tell us that dP by dr is equal to 0. That is, that the pressure should not depend on r and should depend on T only. And so we can rewrite this as a derivative with respect to time of something. So let me erase that and replace that by a derivative with respect to the time. So I'm going to rewrite it as just d by dt, right, of rho r cubed. Rho r cubed is something that is proportional to the pressure term. So minus 3p times r squared times r dot. Okay. So we have these 3 equations, and they're not independent. So it will, in fact, be sufficient to just focus on 2 of them. But nevertheless, some equations are easier to analyze and look at than some others. And so we do have basically 2 unknowns, which are the density and the scale factor, because as I said, usually the pressure is related to the density by some equation of state, so it is not an independent quantity. So the first thing we can do is look at the last equation, right? So we're going to analyze several different cases, and one of the simplest cases to look at is the case when the pressure is 0, right? So that essentially corresponds to non-relativistic matter. Non-relativistic matter has a pressure which is negligible, right? And so we'll set that to 0. And so that means that in the last equation, this term here is 0, right? So we just get that the time derivative of rho times r cubed is equal to 0. And so that equation can be integrated immediately. And so equation 3 tells us that 4 pi over 3 times rho times r cubed is equal to m is equal to some constant. So you can integrate the second equation. And so that tells us that the product of rho times r cubed is a constant, and we call that constant capital M, and we add a constant in front as well. And so that's a useful way of looking at it. And then we can look at, say, the first equation. Right? So I look at equation number 1. Right? And set in equation number 1, let's take just lambda equal to 0 for simplicity. And so we get k plus r dot squared, right, is equal to 8 pi g times rho times r squared, multiplying the equation out by r squared. And so by virtue of the fact that the rho and r are related in this way, this is just 2mg divided by r. Divided by r. Right? So that means that you can write this as 1/2. So let's divide out by 1/2 so that we have the r dot squared multiplied by 1/2, and let's multiply by m2. So 1/2 m r dot squared minus, and so we'll subtract out this term here. So we multiply by m, so we get m squared times g and divided by 2. So it's just minus m squared times g divided by r, right? And this is equal to all the constant terms, right? So the constant term, we're going to bring that constant term over on this side and multiply it by m. So it's minus k over 2 times m, right? So we get this equation. And now what we do is, so that's essentially a rewriting of the first field equation, the TT1, using conservation of energy to use the fact that the density, right, which is of course a function of t, right, and the scale factor, which is also a function of t, have to be related to each other by this equation, right? So now we stare at this equation a little bit, and of course we recognize that this is just basically the Newtonian equation for this dust, right, where the r dot squared is essentially the kinetic energy term, right? So this is the kinetic energy term, and this is the potential energy term, right? And that is equal to some sort of constant, right, which can be regarded as the total energy. Remember that k can have either sign, right? And so what we discovered at this stage is quite interesting, namely that if we look at the field equations in this particular limit, where we have a non-relativistic fluid and we take this cosmological constant to be negligible, we're basically back at the Newtonian equation for the fluid. Right? So this is essentially the Newtonian result. The Newtonian result for a gas cloud, right? And in fact, it was Milne and Macrae that in 1935 showed that you can derive under suitable conditions, the equations for the Robinson-Walker metric that you get from the Einstein field equations for the scale factor, you can derive exactly the same equation using Newtonian physics and they end up being the same form if you consider a gas cloud that is homogeneous and isotropic. So, so that means that really, as far as this case is concerned, we haven't discovered anything fundamentally new, right? If you want, what is new is the fact that there is this constant k, right, which only takes 3 values. Right, but other than that, the equations are very similar to what you would write down in Newtonian mechanics. And so now let's, and this of course was, as I said, just for the simplest case where the pressure is negligible and lambda term is 0. When you add the lambda term, then that is of course new, because there is no such thing as a lambda term in Newtonian mechanics. So the lambda, the cosmological constant term, is an entirely new ingredient that was introduced by Einstein in 1922, and or maybe even earlier than that. And so now we'll come back to the full case. And so let's look at an equation that just gives the acceleration. Right, so I'm going to leave those equations on the other board. And let me write some equivalent form for it. Right. Equivalent form is that we can write r dot over r. The first equation we can well, we'll leave it essentially the same, right? Except we're going to divide out by 3, and we'll isolate the k over r squared term and write it as r dot over r squared plus k over r squared is equal to 8 pi g over 3 times rho plus the lambda term, which is in this case is just lambda over 3 because we divided everything by 3. And well, this part here is going to be recognized in a little bit as essentially the Hubble constant term, right? And this term we isolated because, in fact, present observational evidence is that k is very close to 0. So observation k is very close to 0, which means that the present cosmological data seems to suggest that the models that fit the data best are the ones in which you have a flat universe in which k is 0, right? In which case, of course, this term is equal to 0. Now, the reason why this equation, this TT equation, is useful is because you can see that in fact, it involves the density only, right? This equation does not involve the pressure. So even if you don't know much about what the pressure is, remember that the pressure is related to the density by an equation of state, right? And so, but maybe you don't know exactly what W should be used. And in the case of this equation, you have rho appearing only, right? There is no P. And so the other equation that you can write down is what you get from equation number 2, as I've indicated, substituting the first equation into it for this combination here. So that means that, so this would be like equation 1 prime if you want. And equation 2 prime would be an equation for the acceleration only, right? And so that would give the second derivative of the scale factor, the rate at which this universal expansion is accelerating, that is given r double dot divided by r is equal to minus 4 pi g divided by 3 again. And so now you get a combination of, in this case you have the pressure, in that case you have the rho, so you have a combination of the two, which is rho plus 3p. And of course, the lambda term is still there. It doesn't cancel out, so you get plus lambda over 3 in this case as well, right? So the acceleration is determined by, if lambda is negligible, is determined by the combination of rho and p, right? So generally, you would expect that, in fact, this quantity be positive, so in which case the acceleration would be negative, right? And that is going to be offset at some point by the fact that lambda is positive. Now, it is, in fact, in general, it is possible to have lambda to have either sign, right? Because you remember that lambda was a term that you could add to the field equations, right? But nobody said at that stage that you should pick one sign or another, right? Lambda has to be a number in order for the equations to be generally covariant, right? But it doesn't have to have a specific sign, right? So it could be either sign, but if lambda, of course, is positive, then these two terms will be competing, right? You have a negative one and a positive one, right? The current evidence is, in fact, that lambda is positive. The current evidence is lambda is positive. Now, regarding lambda, it is quite interesting that there is a long, convoluted story about the lambda itself, right? Remember, it was introduced by Einstein in the early 20s, late 10s, because he thought that if we looked at his field equations, right, the solutions would predict an expanding universe, or maybe a contracting one as well, but certainly an expanding one would be one of the natural solutions, and that seemed to disagree with what was observed, right? So he introduced this cosmological constant so that you could get a static solution, one that was not expanding, right? And so he did that around 1922. He worked out a number of properties of the kind of cosmological models based on the Friedmann-Robertson-Walker metric. And well, just about at the same time, around 1924 and up to about 1929, it was Edwin Hubble that actually discovered that if you look at faraway galaxies, they're moving away from us, and the universe as a whole is expanding, right? So there was no need for the lambda term, right? The Friedmann-Robertson-Walker equations, the kind of equations that we have on the blackboard right now, predict naturally expanding universe already when lambda is different from 0. So Einstein thought that this was a major blunder, a major mistake at that time, because of course you introduce a new parameter in the field equations, right? That you don't know what it is, right? It's just some arbitrary parameter. So that was not particularly attractive. So the cosmological constant then kind of lingered along for a number of years with the statement generally that it was consistent with 0, right? And well, when I was a student, a postdoc, and so forth, then everybody would told me the cosmological constant was 0. And the argument for that was, of course, supersymmetry, because if you have supersymmetry, then it would be natural for the cosmological constant to be 0. And so the argument was that in the late 80s and 90s, the cosmological constant was 0 because all these different divergences associated with different types of particles would cancel out, and therefore supersymmetry provided a natural explanation for lambda being 0 until 1999, where in fact people at Berkeley did some and somewhere else, and other places as well, did some very accurate measurements of distant supernovas, right? And they were able to establish with great accuracy how things evolved at very large scales, and found out that in fact lambda is non-zero. Right? So lambda is non-zero. It is a small quantity. It depends, of course, in what units you measure it. But it took a long time to in fact detect it. Right? So it's only since 1999 that we know for sure that lambda is non-zero. Present cosmological models, in fact, have a number which is pinned down quite a bit. I mean, one knows this lambda contribution to within a few %. So it's definitely non-zero. And it is positive, right? So it seems then worthwhile to investigate what kind of effects it gives, right? Now, if you look at this equation, right, then you can see that in fact the lambda acts like another, you can write it as a term which acts like another rho, right? So you can introduce a rho lambda, right? Define that as lambda divided by 8 pi g, right? And then you can write the two contributions together. You can write them as 8 pi g over 3 times rho plus rho lambda, right? So you can consider the cosmological constant as some sort of energy density or matter density of the vacuum. But of course there is a fundamental difference between the rho of matter and the rho associated with lambda. And what is the fundamental difference? Well, of course, the fundamental difference is that the rho for matter goes down like 1 over r cubed because of energy conservation. So as the universe expands, the local density goes down like 1 over r cubed, right? The rho lambda is always the same, right? The vacuum energy density stays the same because, well, according at least to GR, this lambda is a number, right? And the G is a number as well. And so the rho lambda is some constant. So that rho lambda is something like 10 to the minus 29 grams per centimeter cubed, right? You can work it out based on cosmological observations. You can actually say it's so much that the vacuum weighs. So we think of this, at least I think of this rho lambda as a vacuum energy density. And of course, as soon as you talk about vacuum energy density, the idea that comes to mind immediately is some quantum mechanical effects, right? Because in quantum mechanics, it is normal to have vacuum energies, right? We know from the other class that I'm teaching now and from the things that we've seen before that in quantum mechanics, the vacuum is never empty, right? It's populated by virtual pairs, and it does have an energy which is non-trivial, and you can in fact measure the effects of the vacuum energy in a number of different things, including things like the Lamb shift, but even the Casimir effect, right? So it's a well-known concept, and so it is not unnatural from a quantum perspective to have some sort of vacuum energy, and so the lambda is this vacuum energy, and it does have this characteristic, right, that follows from Einstein's equation at this stage, namely that it is a constant. It's always the same through the evolution of the universe. It doesn't change. It's a number, right? So in that respect, its properties are quite different from the rho that is associated with matter, right? Now, the other thing that is that you can check is that if so, let me write that here, right? So remember that the pressure is W times rho, right? And this W can take essentially, well, I would say 2 values, maybe 3, right? And so if W is 0, we have matter. If W is equal to 1/3, we have radiation, right? And the other thing that we can look at is, in fact, a case where you have a cosmological constant. You can model the cosmological constant by having W equal -1. So the lambda term corresponds, in fact, to W equal -1. And so we can write this equation of state, and it is useful because we can then solve the field equations for various values of W without having to go through this exercise independently a number of different times, right? So if W is 0, so that is if we have matter, W is 0, then rho goes like 1 over r cubed from this equation, right? Because the pressure is negligible, and that's what we just discussed a moment ago. If you have radiation, then W is 1/3, as I said, right? And you put, so you put here P is equal to W times rho with 1/3. And so the 1/3 cancels the 3, and in fact this equation then gives that rho goes like 1 over r to the 4th, right? So the density of radiation goes down a little bit faster as the universe expands than it does in the case of non-relativistic matter. And incidentally, when I talk about radiation, that means any sort of ultra-relativistic particle, right? So it could be the photon, right? It could be also neutrinos, right? Neutrinos, for most practical purposes, can be considered as particles that have an equation of state where this parameter W is close to 1/3, right? And we do know that there are 3 neutrino species, so they contribute as well. And so the neutrinos will also have a density which goes down like 1 over r to the 4th, right? So matter per se does not mean every form of matter, but it means non-relativistic, essentially non-relativistic matters like stars, dirt, and things of that type, right? And, well, then we have, of course, the other case, which is cosmological constant, which we're going to treat separately, right? So now we want to compare this to what we observed today, right? So this is what, so far, we've just written down what Einstein's equations tell us. Right? So we now compare to current observations. Current observations. Right? And so that means that we look at what is happening today. Right? We look at what is happening today. And so the time that is associated with today, we're going to call it T0. So anything that has an index 0 somewhere refers to what we observe today. Right? So for example, we can take the scale factor r and the derivative of that and calculate r dot over r. This is something that appears in the field equations in a number of different places. And so that would be the expansion velocity. Right? And so at t equal to T0, which is today, this is what we define as the Hubble constant. Defined as the Hubble constant, right? Now it is clear from Einstein's equations that this is not a constant in general. Right? It is not a constant, right? Because Einstein's equation, of course, involve this combination in a number of places. So for example here, right? And it is clear that that particular ratio has no intention of being the same in time because rho is changing, and rho, in fact, has several contributions from, say, matter and radiation. So Hubble constant, right? Nevertheless, if we look at the universe around us, right, then that number is pretty much the same number. We'll come back to that in a little bit, right? And so the other thing that we usually do is we take r of T0 to be equal to 1. So we use the scale factor today as kind of a reference scale. Right? Set that equal to 1 so that helps us out. We also do know, and we'll come back to this later on, but we do know that pretty much the time today versus the time when things started out is roughly of the order of 13.82 billion years, right? So we know that there is this time scale that comes in, which is related to the Hubble constant. You can see that the Hubble constant, in fact, has dimensions of 1 over time, right? So we now go back at equation 1, right? Remember, we only have 2 independent equations. And so we go back to the first equation, which involves this combination r dot over r, right? And so we're going to rewrite it by isolating the Hubble term, the r dot over r squared, right? And so we're going to write it as, so let me take lambda equal to 0. And so we write it as r dot over r squared, and then minus 8 pi g over 3 times rho. Of course, rho depends on r or on t, right? And so this is equal to minus k over r squared. Right? By the way, don't confuse the r, which is the scale factor, with the scalar curvature. In fact, nowadays in the literature, it is quite common to use for the scale factor a of t. Right, so, and again, a is normalized so that today this is equal to 1, and so this is actually also related to the redshift. Right, so a of t is related to the redshift in this way. There's a very simple relationship which makes the scale factor to be particularly useful. So, so if we look at this equation, then we can ask our question, when is this quantity 0? Right? And so this quantity is 0 for, so we call this combination here, we call that h squared, and of course it depends on t, right? In general, has no intention of being constant. But this is 0 for whenever h squared is equal to 8 pi g over 3 times rho. And so we can solve this. We can solve this for a specific value of rho, which we call rho critical, right? So let's call this rho critical there, right? So rho critical is equal to the Hubble square is equal to 3 times Hubble square divided by 8 pi g, right? And so that is again a quantity that depends on h and depends on the time, therefore, right? So today, rho critical today is equal to 3h squared divided by 8 pi g measured today, right? So it would be a naught there, right? And so we can try to figure out what that quantity is, and rho critical is, if you put in the numbers, it's about 1.88 h squared times 10 to the minus 29 gram per centimeter cubed. So what is h? Well, this h is the h that I introduced last time, namely one writes h naught as 100 times little h times kilometer per second per megaparsec, right? And so this value h is, so the Hubble constant is known with some degree of accuracy, and the latest number, so around 2014, is that this h is about 0.67. So this is around 2014, is mostly the newest satellite data, the Planck data, that gives that value of h. Now, this is kind of a pretext to look at how this Hubble constant has changed over time, because Hubble was the first one to actually determine this rate of expansion of the universe. And he estimated that, little h to be about 5 back in 1929. Right? So the expansion rate that he measured was about 500 kilometers per second per megaparsec. And so that's Hubble's number up here, corresponding to about 1920, right? So then I'll pass this around in a second. So as time went by, people realized that, well, Hubble's number was really high, and that if you looked at galaxies which is further and further away, and you increase your statistics, you would find that actually the universe was not expanding that rapidly, that the number was more like a factor of 5 or maybe even more lower. So over the years, the number started to go down significantly, and then over the last decade, it started to settle down at some number which is around 0.7, right? And the latest data actually has very small error bars, right? And so there has been some controversy over the years, before 1950 or so, on what exactly the value of the Hubble constant today was, right? And so that has to do with the difficulties in trying to fit the recession velocities to a straight line as you look at objects that are further and further away, right? Because the Hubble law predicts some sort of linear relationship between velocity and distance, and so that has become, though, the determinations have become more and more accurate recently. So we do have a pretty good idea of what this little h is, and a result of that, we do know this critical density. Now, the present density of the universe is not the critical density, but it is very close to it, and that suggests that maybe this should be some sort of reference density, right? So as a result, reference density, right? As a result, it might be useful to express, well, the normal density in terms of that number, right? That number, which is presumably pretty well known because one knows the Hubble constant pretty accurately. And of course, one knows G, the value of G, very well. And so as a result, it is useful to set rho, right, which is a function of t, right, as some omega times this critical density, right? And so that omega is a number of order 1. So it is basically the fraction, right? So you can write this omega as rho divided by rho c. Okay. So you define this fraction omega. And that is useful because you can then rewrite this equation. This part here is h squared. This part here is just capital omega times the critical density, right? So we can rewrite the equation as h squared times 1 minus this capital omega, right? 1 minus the capital omega is equal to minus k over r squared. Right. Like that. And the other thing that we can introduce is astronomers and cosmologists, they don't just measure the recession velocity, right, which is this Hubble parameter, but they also measure the acceleration that is associated with that. And so one can define the following quantity, which is q equal to the deceleration parameter, right? And so that is defined as minus r times r double dot divided by r dot squared. Right? So the acceleration parameter has not to do with the velocity, but with the acceleration, the r double dot. Right? And that you can figure out what that is based on this equation, as well as the other equation that we had, which was equation number 2. Right? So this was coming from the RR equation, right? And so we can rewrite this as, well, first of all, it's clear that we have the Hubble h appearing in this combination if we multiply and divide by r squared, right? So this is equal to minus r double dot over r divided by times h to the minus 2, right? And because of this relationship and the field equations, this is just equal to omega, capital omega over 2, right? So that means that in fact, we can measure this omega, we can measure this fraction by measuring the deceleration, right? So this deceleration parameter gives a direct measurement of this omega. But of course, again, we're measuring at today, right, at t equal to t naught. And furthermore, this equation only applies to when you have just one type of matter, which is ordinary non-relativistic matter, right? So what we want to analyze is the more general case where we have, say, so this was also lambda equal to 0, right? So we want to analyze the more general case where lambda is non-zero. So can repeat for lambda different from 0, right? So at least we have a second component that comes in. We do have 3 main components because we have non-relativistic matter, we have radiation, which is photons and neutrinos, and then we have the lambda term, right? The vacuum density. Well, it turns out that actually for most purposes, if you look at the universe today, the radiation component is not very important, because the radiation component is only important when we look at the very early stages of the universe. So, and at later times, what really is most important is the non-relativistic matter and the lambda component. So we're going to focus on those two, right? And so for lambda different from 0, we have r dot over r from the first field equation squared minus 8 pi g over 3 times rho. And then now we have the new term, which is the lambda over 3. By the way, if you put in the speed of light, there is a lambda c squared term there. And so the lambda term is, in fact, a relativistic correction, right? So, well, we have a system of units when lambda is 1, so we don't put the c squared, but that's what we would belong. And so this is equal to minus k over r squared, right? And so again, we repeat the same exercise, that this is just equal to h squared, right? Hubble constant, which is not a constant, right, is a function of t. And in here, if we have non-relativistic matter, we can write that the rho is related to the total mass by m is equal to 4/3 pi times g times rho times r cubed. Sorry, not g, rho times r cubed, right, like that. Right? So we can substitute for rho what we get from this expression. So this is, of course, constant. Right? This is energy conservation. By the way, energy conservation does not depend on lambda. Right? The energy conservation states that T mu nu semicolon nu is equal to 0. So it applies to the energy momentum tensor for matter, whether relativistic or not non-relativistic. And there is no lambda in here. Right? There is no lambda in here. And so that means that that this energy conservation is not affected in any way by the lambda term. And so this argument still goes through because this follows from energy conservation, right? So you can replace the rho by a constant divided by r cubed, right? And so in this case, the rho, right, goes like 1 over r cubed, which means that if you look at late times, right, if you look at late times, then this contribution becomes less and less important than this one. So lambda term dominates at large r or at large t, right? And so in fact, when the scale factor is large or when the time is large, you can integrate this equation immediately. As I said, also k is essentially 0 from observation, so we can take that to be 0. And so r of t then goes like e to the square root of lambda over 3 times t. Right? So in fact, the lambda term gives an exponential expansion of the universe. Very rapid. Right? And that only happens, though, at late time. So that, again, is quite interesting because it shows that if you wait long enough, then the most important term in the field equations is, in fact, the lambda term. At late times, it dominates over everything because the contribution from matter goes down quite rapidly. This rho either goes like 1 over r cubed or it goes like 1 over r to the 4th if you have radiation. And so that contribution kind of falls out. The k is very close to 0, so it's negligible. So if you look at late times, the only term that is really important is this lambda term. So you just have to solve the equations with these two terms, and that's an exponential. Of course, you have plus or minus, right? So you can have an exponential expansion, an exponential contraction, but what is relevant here is the expansion, and that's what we see. So it's interesting that a term which originally was thought to be negligible or even 0, right, is in fact going to be the dominant term. It is already very important nowadays, right, as we shall see, because we can quantify how important it is, and it becomes even more important as the universe cools off. So we can write the analog of that equation, right? So this thing is modified, right? I have the luxury here that I can just erase a few things, right? And so there's an extra term in here if you have the lambda term. So I'm going to do that. So it's h squared minus 1 minus omega times, so minus lambda over 3 h squared is equal to minus k over r squared. And if we apply that, so this is no longer for lambda equal to 0. So if we apply that today, then we put a naught everywhere, right? Right. The field equations apply at all times, and they apply, of course, at the time t equal to t naught. So this relationship has to be satisfied if the universe is made mostly out of non-relativistic matter today and a lambda contribution, right? And the second relationship is also changed when we have a lambda term. So the definition, of course, stays the same, right? The definition stays the same, but the change here is that this is equal to 1/2 times omega naught minus 2/3 lambda divided by h naught squared. So it's changed a little bit. And well, when I put a naught here, I mean that today, right? It could be at some other time, but this q, again, the q has no intention of being constant in general, right? So it will be varying with time, but nevertheless, we can talk about the deceleration parameter as we observe it today, and it is defined precisely by this ratio, and that ratio is also given by this expression, which means that if we measure the deceleration parameter very accurately, then that will give us a handle on the matter fraction, which is this omega, right? Remember, the omega is defined as the rho divided by the rho critical, right? So evaluated today, that is the rho naught divided by rho critical naught. So the measurement of the deceleration parameter will give us a good handle on what this fraction is and what well, the Hubble constant, which can be determined independently, so we're supposed to know what that is, right? So there is this, of course, very interesting question of how you relate the predictions of the field equations, right? The field equations are quite clear. It's quite clear what the ingredients are. But nevertheless, when you want to compare it to observation, there are a number of new issues that come up because, first of all, you don't know exactly what the universe is composed of, right? What fraction is matter, what fraction is lambda. And furthermore, when you talk about the Hubble expansion or the deceleration parameter, you have to be very careful about, you know, at what distance scale, at what time you measure these things, and so forth. So then there is the issue of how you compare observational cosmology to the general relativistic prediction for the homogeneous isotropic metric, right? So now, these are still somewhat general considerations, but we can actually solve the field equations completely. That is, we can solve for the scale factor exactly as a function of time. We have done that here when the universe is dominated at late times by a cosmological constant term, but we can do that in a more general case. So let's do that. Solution for R of t, right? And I should say more general. More general solution for R of t. And to make life easier, we will just write that P of t is equal to W times rho of t, and we're going to analyze each contribution separately. So instead of putting them all together, we analyze them individually, but we do have three cases, right? And so we'll have a W equal to 0, W equal to 1/3, and W equal to -1 for the cosmological constant, right? Which is not a case that we need to fit into this category because we can analyze that separately very easy. But this would be radiation, and this would be non-relativistic matter, right? So if we do that, then we have that the basic equation is that R dot over R squared, right? And is equal to 8 pi g over 3 times rho. Right? That's equation 1 or 1 prime maybe. It was actually 1 prime. And equation 2 prime was equal to R double dot divided by R is equal to minus 4 pi g over 3 times rho plus 3p. Right? And so we are going to use that here, right? As I said, lambda is, I've taken that to be 0, but if you want, you can consider that equation also as applying to lambda, where omega, that parameter W is equal to -1, right? And anyhow, in this case, the solution, you can verify that it is indeed true. You can write that down completely And the solution is that rho of t is equal to 1 over 6 pi times 1 plus w squared times g times t squared. So in all these three cases, no matter what w is, the density always goes down like 1 over t squared, where t is this Friedmann-Robertson-Walker time. And r of t also is completely determined. R of t is equal to some constant, right? Usually we take this constant to be 1 at t equal t naught, and then times t to the 2 divided by 3 times 1 plus w. Right? So you can in fact solve those two equations completely. They're simple enough. And so that means that the scale factor, for example, how that grows in time depends on what type of matter you have, right? And incidentally, I should add one more result, and that is that you can write a rho as a function of the scale factor, because you can replace the time in there. You can solve for the time and plug it into the first equation. And so rho as a function of r goes like r to the minus 3 times 1 plus w. 1 plus w. Right? So in fact, this is in agreement with what they said before, namely when you have non-relativistic matter, w is 0, and the density goes like 1 over r cubed. When you do have relativistic matter, then w is a third, and rho goes like 1 over r to the fourth. Right? So we can make a little plot. Right? So for matter, r of t goes like t to the 2/3. For radiation, r of t goes like the square root of t, right? And for the cosmological constant, lambda, r of t goes like e to the square root of lambda over 3 times t. Right? So the expansion is a power law in the first two cases, but it's an exponential expansion for the cosmological constant. And so, as I said, that means that you can make a plot of r of t versus t. Now, when the universe is young and hot, most particles are moving at relativistic speed. There's a lot of radiation contribution in that era. And so out here, the universe starts out with the square root of t. Right? The square root of t behavior is important. Now, we also saw that radiation contribution, as you go forward in time, goes down like 1 over r to the fourth. The matter contribution goes like 1 over r cubed. So matter eventually becomes more important than radiation. And so that means that there is a period here, right, where things go like t to the 2/3, right? Matter-dominated phase. Radiation-dominated phase, matter-dominated phase. And then when we go to later times, then we have this new behavior, which is that r goes like e to the square of lambda over 3 times t, and the expansion becomes exponential. Right? So you have 3 different regimes, and they apply to 3 different regions. Right? And it happens that we are here now. We are here now somewhere where the radiation contribution is very small. Right? It was important in the early universe, but nowadays it has pretty much died off. The matter contribution is very important, but the lambda contribution is contributing about the same amount. So we are at the stage where we start seeing this exponential expansion due to the lambda, right? And in particular, it's a positive lambda, right? Remember that lambda could have, in principle, based on general covariance, could have either sign. If lambda, of course, was negative, then you would have a complex exponential, which means you would have a sinusoidal type of evolution, right, which we don't. So the present observational evidence is that lambda is a positive number, and the expansion of the universe is accelerating dramatically, right? It's accelerating dramatically because we are going from a phase where the expansion is a power law into a new regime where the expansion is no longer a power but is an exponential. So this, the vacuum is starting to become very important, right? So in a moment we're going to try to put these three things together, right? It's actually not too difficult to do that. And before I do that, though, let me talk about the temperature for a second. Now we saw that the scale factor is related to the redshift. So when you're talking about a given scale factor, you're talking about a given z, right? And so if you go back in time, you're looking at smaller and smaller scale factors, which means you're looking at larger and larger redshifts because the relationship is that the scale factor is 1 over 1 plus z, right? And so what about radiation? So if you look at the radiation contribution by itself, radiation plays an important role in modern cosmology because the cosmic background radiation is measured to great accuracy, right? Both the value of the integrated energy density, but also the anisotropy in the cosmic background radiation. So in the case of radiation, we have P is equal to 1/3 times rho. Right, that's the equation of state for relativistic particles that you can find in Patria that we discussed in the statistical mechanics class. And by the way, it's not possible to have that many different equations of state. Right? If somebody told you that they were using an equation of state where the W is equal to 1/5 or is equal to, you know, minus 0.1, that would be regarded as a very exotic form of matter, because usually matter, you know, if you read through, right, what is accepted, the statistical mechanics physics, you will find that the possible equations of states are actually quite restricted based on the nature of the particles that we know about, right? We know that particles fall into two classes. They're either bosons or fermions, right? And they're either non-relativistic or they're ultra-relativistic. And so you can discuss all these cases with some quite great accuracy, and you come to the conclusion that the number of possible equations of states is not that large, that you basically come down with just these two cases. So from energy conservation, right? From energy conservation, you have that rho of T divided by rho naught is equal to R naught divided by R of T to the 4th power, right? So for radiation, you have the 4th and not and so in other words, rho goes like 1 over R to the 4th. And now you can look at how things behave when you have, say, for example, photons. Photons, then the energy density for a gas of photons is known, right? And the integrated density is, so the energy density, which is the energy density per unit volume, but integrated over all frequencies, right? So this is the integrated Planck distribution, right? Integrated Planck distribution, that energy density integrated over all frequencies is the Stefan Boltzmann law. Stefan Boltzmann, namely that rho is equal to G times pi squared divided by 30 times kT to the 4th divided by h bar c to the power 3. Right? So it was Stefan and Boltzmann that actually determined that the energy density for radiation goes like the temperature to the 4th power. And they determined what the constant was in front. And this was, of course, before the advent of quantum mechanics, right? It was Planck later on that gave us the expression for the Stefan Boltzmann constant in terms of Planck's h bar, right? And so that means that essentially rho goes like T to the fourth, right, when you look at the temperature. And that result is, of course, very nice because we know that the density in the Friedmann-Robertson-Walker universe goes like 1 over r to the fourth, right? So that means that the temperature will go like 1 over the scale factor r of t, right? So there is a linear relationship between, based on the Stefan Boltzmann law, there is a linear relationship between the temperature and the inverse of the scale factor. So the universe cools off as it expands. It cools off in a way that is precisely predicted by this relationship. And what is G? Well, for photons, G is equal to 2. Right? So that has to do with how many degrees of freedom you have for a massless particle. For the photon, you have 2 polarization states. You have 2 helicity states, so G is equal to 2. And if you have neutrinos, then each neutrino has 2 polarization states, but then you have to add the fact that you do have 3 neutrino species, right? You have the electron neutrino, the muon neutrino, and the tau neutrino, right? And of course, those will all contribute in the early universe, right? However many light particles you have, they will be floating around in this primeval soup, and you have to add them all up. That, of course, is not going to change the result that the temperature goes down like 1 over the scale factor, which is a simple result and is one that is fairly easy to remember. Right? And so neutrinos, G is equal to 2 times 3. Right? As far as we know, there are 3 neutrino species. There might be more than 3 neutrinos, but the additional neutrinos must be really heavy because otherwise they would have be seen at LEP. Right? The LEP experiment at CERN set a very stringent bound on the number of light neutrinos, which is 3. Right? And so if there's other neutrinos around, then they have to be heavier than whatever LEP could see, right? LEP went up to an energy which was, I think, 200 GeV. So let's now come back to trying to combine these things together into one single equation, right? And don't want to repeat what I already said, right? Don't want to repeat what I already said. So we introduced this critical density. We introduced the Hubble constant, maybe today, maybe at some other time. This also depends on time, right? Let me rewrite what the result was that the critical density, so h naught squared, was equal to 8 pi times g divided by 3 times this rho critical, right? Today. Right? And so now we can introduce the following quantities. So we want to write the field equations in a way that includes all these 3 contributions, right? We kind of analyzed them separately because it was easier to see what happened if you look at them individually. Radiation, matter, lambda. Now we're going to combine them all together into a single equation, which is not that bad. It's actually quite nice, but let's do this. So we first introduce the matter fraction. Matter fraction, so that is the density of matter, right? And well, let's say today, right? Today, and divided by this rho naught. So let's call this rho naught, which is the critical density today, which is something that we can estimate based on the knowledge of the Hubble constant today. Right? So omega m is the matter fraction, and then we have the radiation fraction, omega r. Right? And so that is defined along the same lines. It's going to be the density of radiation, density of radiation rho r of today of T naught divided by rho naught. And finally, the cosmological constant can be forced to have the same form, right? Because we can write this as, and so omega lambda, we're going to write it as omega v, v for vacuum, right? So vacuum fraction. And so that is rho lambda, or rho v, today divided by rho naught. Right? Now you remember that rho is equal to lambda divided by 8 pi g. That was our vacuum energy, right? Or you can call it rho lambda, you can call it rho v. It's the same thing, right? Right. So that is a constant. That is a constant. So this thing is supposed to stay constant. Of course, unless something strange happens and whatever they see as a lambda term turns out not to be a lambda term, but that would, of course, could cause problems with general covariance. Now, because of the way, now the interesting fact is that one knows, right, based on current cosmological observation, that this part here is only about 5% is atoms. That is normal matter, right? And about 27% is dark matter. That is matter that is non-baryonic. It's not made of the usual things that we are made of, atoms and protons and electrons and so forth. That, of course, all goes into the matter part. The radiation part nowadays is quite negligible. And the interesting aspect is that if you write it in this way, then this fraction amounts to about 68%. That's from the latest Planck data. It's about 68% of the fraction of energy density in the universe is due to this vacuum energy, whatever it is, most likely a cosmological constant. So if you write it in this way, then you have, of course, that omega m, because it's normalized, you have that omega m plus omega r plus omega v is equal to 1. Right? So the other thing we know is that they behave differently as a function of the scale factor. So we do know that from what we discussed previously, we do know that omega m goes like 1 over r cubed, that omega radiation goes like 1 over r to the 4th, and that omega vacuum goes like, well, 1 over r to the naught. Right? 1 over r to the naught is a constant. Right? So they behave very differently. And so that, again, we pick the scale factor r of t naught to be equal to 1. And so we can define rho of r in the following way as rho naught times all the different contributions to it. And well, the first contribution is the vacuum energy, right? That appears in the field equations. You can write it as a rho, and you can write it in this way, right? In fact, it's kind of a trivial rewriting, because because of rho lambda, right, rho v equal to lambda divided by 8 pi g, so that is a constant. Right, so this part is a constant part. And then you can write it as plus omega, the matter part divided by r cubed, and the radiation part divided by r to the 4th. And so if you define it in this way, then you can get from the field equation, in particular, again, we're talking about field equation number 1, which is the one that involves just the density, right? Then that equation is that r dot squared minus 8 pi g over 3 times rho. Well, the rho here is rho naught times this part here that goes in there. Right? And that is equal to 0. And that is, in fact, the correct equation when k is equal to 0. So you can write it in this form. And the reason why you want to write it in this form with this rho of r is because it looks like a potential. That is, we can rewrite it as so this part here is nothing but h naught squared, right? And this, by the way, is always evaluated at, so we can write this as 1 over 2 h naught squared times r dot squared plus some effective potential which depends on r, and that is equal to 0 because we've taken k to be 0. And so that looks like a classical mechanics problem because you have the velocity part and you have an effective potential. We've divided out by the Hubble constant so that the potential is just an expression in brackets. So U effective is equal, well, we also divided by 2. And the other thing is that the potential always has a minus sign in front. So the potential is equal to minus a half, right, times omega v times r squared. I think I lost an r squared here. There's an r squared here. Sorry about that. Right, because sometimes we write this piece as h squared and then it's r dot over r squared. So we multiply the r squared. So there's an r squared here. So it's omega v times r squared plus omega matter divided by r. And then plus the radiation part, which is omega r divided by r squared, and then close parenthesis. And so this is a U effective of R. And so we can treat it as a classical mechanics problem, right? Because now we can plot what this U effective is, R, as a function of R. And what we see is that when we go to small r, of course, the part that is dominant for small r is the 1 over r squared, right? And that has a negative sign. So there is the minus 1 over r squared that is due to the radiation field, which is important at small r. And then when you go to larger r, the part that eventually dominates is the cosmological constant term, the vacuum energy, and that also has a negative coefficient. And in between, of course, there's the matter part. And so it then goes like this. So this is the minus r squared contribution from the vacuum energy. So it now depends on which region you're at, right? Because if you add the integration constant, it would be constant on this side. Here the constant is 0. But nevertheless, this looks like a classical mechanics problem where you have an inverted potential. And interestingly enough, there is no centrifugal barrier term, right? Normally when you have this kind of classical mechanics problem where you go to sufficiently small r, there is a barrier that goes up here, and this is not the case here. There is no centrifugal barrier term. But nevertheless, it looks like a bit like the classical mechanics problem. And well, the end result of that is what I advertised before as being, of course, the correct result is that if you look at the scale factor r as a function of t, you have this behavior that looks like this, right? Where this is the square root of t, the square root of t for radiation, the t to the thirds for matter, and the e to the plus square root of lambda over 3 times t for late times. So this gives the same result, except that now you're putting all the 3 contributions together. And of course, you can integrate this equation easily by just solving for r dot dr by dt, and then solving for dt and integrating. So you solve this problem by the same procedure by which you analyze a classical mechanics problem, and that provides a complete solution to the field equations, assuming that you have, in fact, 3 types of contributions, right? Matter, radiation, and lambda, and assuming that you have the Friedmann-Robertson-Walker metric, which is a homogeneous isotropic metric, as a background to start with. This is what the field equations gives you, right? And so it's then a question, as I said, of determining exactly what the parameters are based on cosmological observations. So nevertheless, this is what Einstein's equations give you. And so anyhow, I think this is all I wanted to say today. So do you have any questions?
Is there anything in the field equation says that g or lambda could not be functions of time?
Right. So that is a very good question. I think the question comes up in a number of instances when I teach this class, right? Because now you could have, right? So one of the concerns is, of course, what kind of deviations could you have from this equation? Of course, you're assuming the homogeneous isotropic metric, which depends on r of t. So if you want to go beyond that, you have to do this expansion, right? So you have to say that g mu nu of x is equal to some g bar mu nu plus an h mu nu of x, where this is the Friedmann-Robertson-Walker background, and this correction is small, right? And in principle, GR gives you what this correction looks like. In fact, it's a rather interesting calculation of looking at matter density perturbations to first order in H, given this correction, right? But nevertheless, the original equations are the one we solve is r mu nu minus a half g mu nu r minus lambda g mu nu is equal to minus 8 pi g times t mu nu, where this is some perfect fluid, maybe with some corrections to it, and we have this term. So now the question is, of course, what happens when lambda is a function of time, right? You might think, right, this is what James asked, is what happens if you now say, well, you know, it could be that this lambda had a different value during the early stages of the universe, and maybe at that time it was a bit bigger, and then as the universe evolved, the lambda got smaller, right? That's certainly a legitimate question to ask. Nevertheless, we would imagine that at this point, based on the beauty and elegance and compellingness of the general theory of relativity, that we would be able to make some statements, because based on general covariance, right, which is the principle that underlies the derivation of this equation to some extent, in addition, of course, to assuming that you don't have derivatives which are higher than the second order, the principle of general covariance would tell you that this is not possible. Not possible because this, of course, violates general covariance, right? You cannot have certain, well, it even violates Lorentz invariance, right? But you cannot have a function of t, right? So what you could have is, of course, a lambda that depends on x, right? What you could have is a lambda that depends on x, where x is x mu, right? And, well, if you do that, then this would be a new scalar field. Right, then what you end up in the simplest possible scenario is that if lambda is a function of x, then you seem to have a new scalar around, right? Okay, and that new scalar presumably, though, has its own field equations of some sort, and if it does have its own field equations, right, because there would be a kinetic term somewhere, right? There would be a kinetic term for this lambda, which would be something like this, right? Right, in the field, in the action, and therefore in the field equations. And that brings us back to the Brans-Dicke theory, right? Because the Brans-Dicke theory was precisely one of those theories where you had an additional scalar. That scalar was massless. So theories in which lambda depends on t violate general covariance. Theories in which lambda is a function of x, then that would be scalar tensor theories, and they would have to be analyzed in terms of those. And of course, the problem with scalar tensor theories, what is the problem with them? The problem is that they seem to be excluded on the basis of solar system observations, right? So there's significant constraints, because if this new particle is indeed massless, right, because otherwise it doesn't really do a whole lot, then you would have problems with. So the question is open. Does the Brans-Dicke scalar exist? Are there, you know, fifth forces in nature associated with new scalar? And maybe not, right? And the scalar, of course, has a potential as well. Now, the same arguments, of course, would apply also to the g of x, right? You could do the same thing. Again, you cannot have, right? You cannot have a lambda of t, because that would violate general covariance, but it could be a coordinate scalar. You cannot have a g of t either. That would tend to violate general covariance too, but you can have a g of x. And so these are all legitimate questions, because in fact you could have that Newton's constant depends on the scale, like the couplings in quantum electrodynamics and in Young-Mills theories. The couplings do depend on scale. We, for example, know that alpha, the fine structure constant at laboratory scales, is 1/137. But if you look at what alpha is at the scale of the Z mass, it's 1/129. So the fine structure constant actually does change with energy scale, with distance scale. And the same could be true in gravity. In fact, I think there's arguments that that should happen. If you have a quantum theory of gravity, the coupling constant will tend to evolve with scale according to the Kalan-Simanczyk equations. But nevertheless, so there are constraints based on general covariance that you cannot have just a function of t. That would not be a good thing. And of course, general covariance could be violated, right? It's always possible that fundamental laws that we believe in, you know, have their limits. But I think, nevertheless, we would imagine that based on what we discussed in this class, that general covariance would be a very compelling argument, right? That this principle that underlies general relativity is that different observers describe physics in terms of the same equations, and that it doesn't matter whether this observer is accelerating with respect to another one. The fundamental equations are the same. So if you insist on that principle, right, then you can't easily have a lambda of t. It will immediately violate all of that, right? Whose t is this? Whose time is that? My time is different from yours. Depends on the coordinate system, right? If it's a scalar that depends on x mu, right, this is of course x mu, that's what we mean by that, right? Then things, you know, there's room there, right? And then it becomes a field, a scalar, right? It doesn't have any Lorentz indices, so it's a scalar, it's a coordinate scalar, but presumably does have some terms in the action that describe it. I should also add that string theory, right, predicts the existence of a scalar field called a dilaton. That is, if you look at the way string theory eventually comes down to four-dimensional space-time, and you look at the long-distance limit when the size of the string is very small compared to what other scale you have in the system. It is a generic feature that string theory gives some surviving degree of freedom, which is this dilaton, which is very much like a scalar, right? And so that dilaton could be there, right? Could be there. So in fact, string theorists have tried to understand whether that dilaton in fact has a mass or whether it is massless. Generally, if it is massless, then you run into problems with solar system observation. So the belief is that though that dilaton field is in fact massive, and the mass of the dilaton is supposed to be associated with the scale of supersymmetry breaking, and whatever that might be, you know, could be 10 to the 17 GeV, it could be lower than that. So it starts to get a little bit speculative, but nevertheless, your question is a very good one, right? It opens a number of different possibilities, and nevertheless, we should think what the theory actually allows and what it doesn't. And there's certain things it just doesn't allow. Any other questions? All right, so I'll see you on Thursday.